this class we'll study deadlocks. So what is the meaning of deadlock? As you know, the process unable to work, then it is said to be in deadlock position. Now why this deadlock problem arises? If a set of blocked processes, each processor holding a resource and waiting to acquire a resource held by another process in the set, then this situation is known as deadlock. So you can go through the bridge crossing example. Whenever a bridge is there, a lot of vehicles are to be passed through that bridge. So they have to go one by one, and while one vehicle is passing through the bridge, others are to be in waiting state. The same thing will follow in a system model. If the resource types are present R1, R2 to Rm, so M resources are there. What are the resources? For example, CPU cycles, memory space, input out devices, etc. Each resource type Ri has deploy instances. Instances means they can fetch some informations. Each process utilizes a resource such as request, use, or release. Now deadlock arises if four conditions hold simultaneously. The first one is circular wait, mutual exclusion, hold and wait, and no preemption. For circular wait, if there exists a set P0 to Pn of waiting processes such that P0 is waiting for resource that is held by P1, and P1 is waiting for resource held by P2, and so on. Then they are maintaining a circle-like position, waiting for the resources. So that's why it is known as circular wait. Now mutual exclusion, only one process at a time can use the resource. No two processes are allowed to use the resource. Then hold and wait, where a process holding at least one resource and waiting to acquire additional resources held by other processes. And the final one is no preemption, where a resource can be released only voluntarily by the process holding it after that process has completed its task. To that point, other processes are to be in waiting state. So deadlock arises. Now we'll go to resource allocation graph. How the resources are allocated to different processes or processors. that is indicated by a graph known as resource allocation graph. How the resources are allocated to different processors. Now for this we have to find a set of vertices V and set of vertices E to define the graph. Basically, resource allocation graph is a directed graph. Here V is partitioned into two types. The P considering all processes in the system, and there are n number of processes, and R considering all set of resources, and here they are having m number of resources. Then request heads given by directed heads, that is P1 requiring the resource Ri or R1. If that is P1 gives a request to find the resource or to get the resource Ri or R1. Assignment heads, or this is also a directed heads, that is R1 is assigned to P1 or Ri is assigned to Pi or any I. That means the heads have a direction. That means this resource Ri is assigned to the process Pi. Now to define the graph, we will define the process by circles and resources by the squares. If the resource are having 4 instances, then we are having 4 small squares inside the big square as shown in the graph or figure. If Pi requests the instance Rj, then we will have an edge from P to Pi to Rj, having a direction from Pi to Rj. If Pi is holding an instance of Rj, then edge will be connecting from Rj to Pi, having the direction towards Pi. Now we'll have some resource allocation graphs as given in the example. We are having 3 processes and 4 resources. In this graph, we can find a allocation. Here P1 requesting the resource R1 where only a single instance is there, and R1 is allocated to P2. While we go for R2 resource 2, that is R2, where 2 instances are there. One instance is allocated to P1, other is to P2, and the instance present in resource R3, P2 is requiring the instance present in R3 but is allocated to P3. So this is one example of resource allocation. Now we'll have some deadlock situation. For this, from this graph, we'll find how a deadlock is created. The same 4 types of resources with different instances with three processes are present. Now from this graph, we are having a cycle and having a deadlock. But if a cycle is present, then deadlock may not present. We will have some example here. This is resource allocation graph with a cycle, but no deadlock is present. Because all resources has been allocated to the resources as per their requirement. But in the previous case, some instances or resources are not allocating to the processes requiring it, so deadlock arises. So here, even if a cycle is there, all processes are having the resources as per the requirement, so there is no deadlock arises. So the basic facts: if a graph contains no cycles, then there is no deadlock present. If a graph contains a cycle, then we have deadlocks depending on various situations. If only one instance per resource type, then deadlock arises. If several instances per resource type, possibility of deadlock is there, possibility, not sure. Now we'll find methods for handling deadlocks. How to handle deadlocks. First, we'll ensure that the system will never enter a deadlock state. The second case, allow the system to enter a deadlock state and then recover. The third case, ignore the problem and pretend that deadlocks never occur in the system. Now, how to ensure the system will never enter deadlock state? We have to find deadlock prevention or deadlock avoidance. Now, first we will go to deadlock prevention. Now, how to prevent deadlock? The methods are there. That is, first one is mutual exclusion. It is not required for shareable resources and must hold for non-shareable resources. Hold and wait must guarantee that whenever a process requests a resource, it does not hold any other resources. So for this request process to request and be allocated all its resources before it begins execution, or allow process to request resources only when the process has none, or in other case low resource utilization or starvation possible here. Then no preemption. So third one is, if a process that is holding some resources request another resource that cannot be immediately allocated to it, then all resources currently being held are released. Preempted resources are added to the list of resources for which the process is waiting. Process will be restarted only when it can regain its old resources as well as the new ones that is requesting. The circular wait, which imposes a total ordering of all resource types and require that each process requests resources in an increasing order of enumeration. Now go deadlock avoidance. How to avoid deadlock? This requires that a system has some additional prior information available. The simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. Deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be circular wait condition. Resource allocation state is defined by number of available and allocated resources and the maximum demands of the processes. So what do you mean by safe state? When a process requests an available resource, the system must decide if immediate allocation leaves the system in a safe state. System is in safe state if there exists a safe sequence of all processes. The sequence P1, P2, Pn, a number of processes are there, then the sequence is maintaining. Is said to safe if for each Pi the resources that Pi can still request can be satisfied by currently available resources and resources shared by all Pj such that j less than I. If Pi resource needs are not immediately available, then Pi can wait until all Pj have finished. When Pj is finished, Pi can obtain needed resources, execute return, allocate resources and terminate. When Pi terminates, then the next process Pi plus 1 can obtain its needed resources and so on. So we'll have a safe state. So basic facts lying behind this: if a system is in safe state, then no deadlock will arise. If a system is in unsafe state, then possibility of deadlock will be there. If avoidance will be there, so if you are avoiding deadlock, then you ensure that system will never enter an unsafe state. So graphically, how to segregate safe, unsafe and deadlock state. If the system is in safe state, then no deadlock will be there. But if it is in unsafe state, then deadlock may arise. And go to resource allocation graph algorithm. How the resources are to be assigned or allocated to processes. The claim aids, that means how the process is claiming the resource, denoted by directed aids from Pi to Ri, from Pi to Ri or Pi to Rj, which indicates that the process Pi may request the resource Ri represented by the dashed line with an arrow. The claim edge converts to request edge when the process requests the resource. When a resource is released by process, assignment edge reconverts to claim edge. Resources must be claimed with priority in the system. Now, this graph represents the resource allocation graph for deadlock avoidance, where we are having P1, P2 are processes and R1, R2 are resources. And the claiming edges are defined by frequent edges, allocated edges and claiming edges. Unsafe state in the resource allocation graph, since they are having a cycle. I will go to Banker's algorithm. Which is very much famous for deadlock avoidance or deadlock prevention. Here multiple instances are there. Each process must have prior claim maximum use. When a process requests a resource, it may have to wait. When a process gets all its resources, it must return them in a finite amount of time. Now, how the data structure available for the Banker's algorithm? If n is the number of processes and m is the number of resource types, then available is the vector of length m. If available j you are having it is equal to k, then the meaning is there are k instances of resource type Ri or Rj available. Then maximum defined by n plus m matrix. If maximum of ij is equal to k, then the process pi may request at most k instances of resource type Rj. Allocation matrix, that is n plus m matrix. If allocation with ij is equal to k, then pi is currently allocated k instances of Rj. So need matrix is a n plus m matrix. If need of ij is equal to k, then pi may need k more instances of Rj to complete its task. So need ij is equal to maximum ij minus allocation ij. That is need is equal to maximum minus allocation. Now Banker's algorithm part on the safe algorithm. The algorithm. So we'll have an example of Banker's algorithm. How to apply Banker's algorithm on some resources and processes. Suppose you are having 5 processes P0, P1, P2, P3, P4. Three resource types, that is A, B and C, where we are having 10 instances in resource type A 5 instances in resource type B and 7 instances in resource type C. So for a time T0, the allocation of the instance resources ABC with the processors P0, P1, P2, P3 and P4. We are having P0 with allocation of instances. We are having maximum instances and available instances. This is the sharing of instances by the processors at time T0. Now study, is the system is in safe state? Now for this you will find the need or maximum allocation and need of the resources for the processes. Now for this you are finding the sequence P1, P3, P4, P2, P0. If the sequence is activated or allowed, then the system is in safe state. Now the example P1 request is how we are finding the availability, allocation and need matrix of the processes, and we are finding different sequences. Now how to find deadlock detection? To allow a system to enter deadlock state, detection algorithm and recovery scheme. We'll discuss these three in this section. So detection algorithm are having wait for graph. We will use a different variant of resource allocation graph for detecting deadlock called wait for graph. So what is wait for graph? In this graph, nodes are processes and adjust denoting Pi to Pj. If Pi is waiting for Pj to release the resource that Pi needs. And the edge Pi to Pj exists in wait for graph if and only if the corresponding resource allocation graph contains Pi to Rq and Rq to Pj for some resource Rq. Periodically invoke an algorithm that searches for a cycle in the graph. A cycle in the wait for graph implies deadlock. An algorithm to detect a cycle in a graph requires an order of n square operations where n is the number of vertices in the graph. We are having one example. Delete 1 is a resource allocation graph where we are having 5 processes and 5 resources. In allocation, edges are given. Now, if we are finding the weight per graph of the corresponding given resource allocation graph, we will find like this with 5 processes with edges connecting to the different processes which indicate the weight for graph. Now the several instances of a resource type is available. Allocation, request. I will go for detection algorithm. Now how to find recovery from deadlock. It is about all deadlock processes, about one process at a time until deadlock cycle is eliminated, or you have to find criteria to select the order of about process. They are priority of the process, how long process has completed and how much longer to completion, resources the process has used, resources processes needs to complete, how many processes will need to be determined, and is the process interactive or bench. So recovery from deadlock will find resource preemption while selecting a victim and preempting resources from that process. A rollback process where return to some safe state, restart process for that state. And last one, starvation may occur. The same process may always be picked as victim, include number of rollback in cost factor.